Okay, hi again, and welcome to part three of this video series on logic gates. And previously, I taught you the basic gates, right? I taught you there's the NOT gate, the OR gate, the AND gate, the NOR, and the NAND gate. Yeah, so there are many different kinds of gates that you can use depending on the situation. There is something called a universal gate. I'm not going to teach you anything new because this universal gate is actually made up of the gates that you already know. So what I mean by universal gate is that I can use these gates, namely the NAND gate and the NOR gate, to build all other kinds of gates. Yeah. So if I want to use a NOT gate, I can actually use a NAND gate to build a NOT gate. If I want to have an AND gate, I can actually use a NAND gate to build an AND gate. If I want to have an OR gate, I can actually use a NAND gate to build a OR gate. Okay, so universal gates are gates, just remember, are gates that can be used to build all other kinds of gates. Universal means it can build all the other gates, basically. All right, so there are two universal gates. You can choose either to use a NAND or a NOR gate. Doesn't make a difference. It's the same anyway, depending on what's in the cupboard, right? Okay, so uh, you have to remember how to draw and how to build the other gates using the universal gate. So let's take a look at the NAND gate first. So if I want to build a NOT gate, using a NAND gate, all I do is that I short the input of the NAND gate. So I short it to make it a one input, and the output will give me the opposite of the input. Okay, if I want to build a AND gate using NAND gates, I put two NAND gates front and back, and I build it this way. Okay, if I want to build an OR gate using a NAND gate, I'll put three, two followed by one. So you have to remember how to draw this. Okay, this one nothing to understand, just remember how to draw. And you can do the same using NOR gates. Same thing, just remember the pattern. It is quite simple. For the NOT, both are actually quite similar. You don't have to remember anything new. And this one, you just have to remember that the and or is the opposite. So you notice that if I'm using NOR gates, the OR is actually the 2. But if I'm using NAND gates, the OR is actually using 3 NAND gates. So just remember how to draw the gates using universal gates. Okay, I'm going to show you an example now. Um, This can be found in page 285 of your textbook. This is review question 11.3. So the question is, substitute each of these gates using only NAND gates, yeah? And I want to simplify to as few NAND gates as possible. So this is what I have to do. I have to work out one by one. Now this is a NOR, right? A NOR is actually a OR followed by a NOT. Okay, a NOR is actually a OR followed by a NOT. So you have to know that. So let's draw a OR first. Okay, so I'm going to replace this one first. I'm going to do this one first. Yeah. So let's draw this over here. So I'll have 1, 2, and 3. Okay. And this 2 will go into here. This will go into here. And these two are shorted together. So I'm going to short it. Now, I'm having great difficulty drawing straight lines. If you are following at home, you have to use a ruler and a pencil with straight lines. Okay? So I've settled the OR. But don't forget, this is a NOR. So I have to draw a knot in front here. So a knot, if you remember, is just like this. Okay? So this is a knot. See? This is the same as this. So I've settled this gate. Now let's draw my AND gate. So N is 2, 1 in front of the other. So let's draw that now. So the way I'm going to do this, that I'm going to draw this in line. So this 2 in front of the other. So I'm going to do it like this. This is going to be shorted like this. And I'm going to have the 2 inputs here. Now you'll be going, whoa, there are 3 inputs. How come I ended up with 4 inputs? Don't worry. This first input is going to be shorted to the second input of your NOR gate. So I'm going to have a shorted input here. Therefore, this is my A, this is my B, and this is my C. Okay? Now, next, there is another OR gate here. So I'm done with the AND. So this is your AND equivalent. I now have to draw my OR gate. So if you remember one more time, the OR gate is 3, the pattern of 3. So let's draw 3 here. So let's draw 1, 2, and 3. Okay, like so. So I know this fella comes here, this fella comes, sorry, what am I doing? Apologies for this, because I hope some of you are quick enough to spot my mistake. This is like this, and then it comes there. Okay, and this comes here, this goes there, and finally I have my output of X. Okay, so this is actually done, completed. All right, so I've completed drawing this whole circuit only using NAND gates. So if you notice, I've done all this only using NAND gates, right? But they want as few NAND gates as possible. So this is where I can start canceling stuff. How do you mean by cancel? Now, this is a NOT gate. So let me do this. This is a NOT gate. Yeah. So if you see a NOT gate, this is exactly this. This is another NOT gate. See, it is exactly the same NOT gate. So this is where a NOT of a NOT will give me the original. Now, if you don't believe me, let's try it out. Let's say the input here, for example, the input here is a 1. NOT of a 1 is a 0. Okay, so this 0 goes into the next NOT gate, and the NOT of a 0 is actually 1. So I land up with what I started off originally. Can you see? I started off with what I had originally. So why put in 2 gates that will give me the original anyway? Yeah, so what I can do is that I can actually simplify this by canceling out these 2 gates. And I also spot one more NOT gate here followed by another NOT gate here. So it's the same principle. Why put in 2 gates to give me the exact same input that I started off with anyway? So I can cancel out these 2 fellas. So what I can do is that with these 2 fellas gone, I've actually reduced my whole circuit by 4 gates. And if I redraw it, it's going to be a lot simpler. I'm just going to draw this here. It's going to be a lot simpler, like so. Here, here, this 2, like this. This is my input, and this is the one solitary gate now I have here. This is still shorted to B, right? This is still shorted to B, and this is my third input, C. These 4 are now gone, and I'm left with just one more gate here. Input coming from here, and the input coming from there. And this is my output, X. Okay, so this is how I built this equivalent circuit using only NAND gates and using the fewest NAND gates possible. So this is my final answer. Okay, so I think a lot of you are wondering why use universal gates at all? I mean, why can't I use a AND, a OR, and a NOR? Why go through all the trouble of using 1, 2, 3, 4, 5 gates? Now, it's about cost. So each gate resides on one type of IC chip. So here I have to use a minimum of 3 IC chips. 3, 1, 2, 3, because I have 3 different gates. This one, if I'm using all the same gates, I can use 1 IC chip. Okay, maybe I have 1, 2, 3, 4, 5. I might have to use 2 IC chips. But at the end of the day, using 2 IC chips is still less than using 3 IC chips. Yeah, so the whole thing about using universal gates is that it lets you use less materials, thereby cutting costs. Okay, so I hope you know how to summarize. You must know universal gates are gates that can be used to form other gates, any other gates. You must know how to draw not and or using NAND universal gates. You must also know how to draw not or and using NOR universal gates. Next, you must know how to draw the equivalent of different circuits using universal gates, and you need to know how to simplify them. Basically, whenever you see 2 NOT gates, one after the other, they can be cancelled off, simplifying your circuit. Okay, so this is the video about universal gates. There are some practice questions in your workbook as well as your textbooks. Look through them and practice, get used to drawing universal gates, and I will see you in video 4 shortly.